And welcome back, everyone. So let's take a look at those radial distribution functions as we continue to start to think about how we describe the orbitals and the wave functions, those solutions to the Schrödinger equation for the hydrogen atom. So here's a figure that's taken from the Macquarie textbook that we're using in our class. And the title is The Probability Densities Associated with the Radial Parts of the Hydrogen Atomic Wave Functions. And so what we see here are on the x-axis, we have r over a naught. That's basically saying that the x-axis is in units of the Bohr radius. So we have 25 Bohr radii at this point. And so because of that, we also need to account for that by dividing the y-axis value by a naught squared. So we're kind of normalizing it for the Bohr radius. So those are the axes that we care about. A couple of other things to note. If we look at the 1s orbital, we can start to see that effectively we have this r squared increase in here on the left hand side. And of course we gradually have this kind of exponential decay. My drawing's not as good as the one in the diagram, but we have an e to the minus r term that brings it back down to zero as we approach infinity. A second thing to note is the number of nodes that we have. And so the number of nodes we have is always equal to n minus l minus 1. So we can say, well, how many nodes do we have in the 2s orbital? Okay, so we have a look at the 2s orbital up here. We say, well, there's a node right in here. Okay, that's the only node we see. So again, remembering 2s, well, the 2 is the n number, and the s represents L is equal to 0. So we have 2 minus 0 minus 1, and that's equal to 1 node. And there's our single node right in here in the image. Okay, and we can similarly have a look at the 3p orbital. So the 3p orbital in here, again, n is equal to 3, and it's a p orbital, so that means L is equal to 1. And so we've got n is equal to 3 minus L is equal to 1 minus 1, and that's equal to 1. And so we therefore have one node, and that node appears right in here. So if we take a look at this figure, we can get an appreciation for what the radial functions do as we move further away from the nucleus. But again, it's important to recognize here that it's an r squared term and an exponential. Of course, there's also the polynomial that comes from those Laguerre polynomials. But this is a probability. So this is the probability, and right here we recognize the probability around a naught, the maximum probability of where we might find an electron in the hydrogen atom. And the other thing to recognize from these images is that the distribution of probability is actually not finite. So it's actually spread out over a large distance away from the nucleus. And that's something that we recognize in quantum mechanics is very different to the Bohr model. So in the Bohr model, we had the electron restricted to a fixed orbit, fixed distance from the nucleus. That's indeed not true, and we found that from the chemical activity 7 exercise that you did last week. So the radial parts of the wave function are actually very easy to display. These are, of course, the probabilities. So what about the actual radial wave functions themselves? Let's have a quick look. So note that in figure 7.3 from Macquarie, we also have some descriptions of the radial wave functions. In fact, these simply are the radial functions here in the top row of images. And then we have the wave functions squared down here. And you're going to see, well, yes, of course, now we have a peak right at r is equal to 0 in here. And that peak at r equals to 0 is because we now no longer have this r squared term multiplied by the wave function squared. So that r squared term is gone, so we don't have the 0 point at the beginning, and therefore the maximum value for those wave functions, or the wave function squared, is right at r equals 0. And so here I just want to draw your attention to the difference between simply the wave function squared and the r squared wave function squared, the r term that ends up being the probability of finding that electron. So that's associated with this r squared psi squared term. So those are the radial parts of the wave function, easy to display. So what about the angular parts? We'll go there next.